sorry, I got a bit distracted, triggered by morphology and the design of humanoid robots. Okay. Any other questions? Okay, then we should do the last two items for time and space, namely specifying time requirements and satisfying them, of course. So, specifying time requirements, we have to have some terminology. You have maximum delay, and yes, you also have a minimum delay. This usually comes a bit as a surprise for somebody new to real-time systems, but delays have a minimum and a maximum time span. Minimum delay until something happens, exactly the same reason as any other real-time system. It has to happen at a specific time, or has to start at a specific time, not earlier, not later. Hence you have, of course, a window in both directions. Of course, you have something like a deadline. You all have some idea what that means. And maximum elapsed and maximum execution time. Maximum execution time is exotic. I'm just mentioning that for completeness sake. Usually in real life, nobody cares about the maximum execution time unless you have a real-time system magically running on a supercomputer and you pay for your CPU time or something like that. That's usually not a major concern for you because you have, especially today, plenty of CPU time. Anyway, that's not much of your concern. Once you activated your task, then all your time scopes become no longer a range, but an individual point in time. You just let this run, including some suspension and reactivations, and you compare whether this is still inside the window of your elapsed time or your total deadline. And you can also add up your execution times. Okay. I think that's all straightforward. I just wanted to nail down some terminology. The next set of terms is a little bit more complicated. Even though it sounds simple, this is actually much harder. Those are the common temporal scopes defined in every textbook on real-time systems you can possibly find. Always nicely managed as periodic, aperiodic, sporadic, transient. Those are the basic time scopes. Periodic is easy. And we like to have all of our stuff strictly periodic. This makes your life easy. Why? Easy to predict, easy to schedule. Simply the algorithms, which we will discuss in a few weeks, about how to come up with a schedule for these kind of time scopes, they're reasonably straightforward if you have purely periodic tasks. If these periods are divisible by each other, it's even easier. But if they're periodic, that's a good starting point. Then you have usually also aperiodic events. Aperiodic means not that they only occur once, but they appear only on average with a certain regularity. So you have to cater for enough resources that sometimes it comes every second, and then there's a second gap occasionally, and then comes every second again. You have to cater with enough resources to do that. This is still not that hard. You can, for example, just assume this is roughly periodic, and I have also always a bit spare resource to cater for that. The actual sporadic events, transient events, they are the hardest because they are orders and orders of magnitude out of the frequencies and the analysis which you do for the rest of your system. They happen once in a lifetime from the perspective of a fast real-time system working usually on the clock rate of some on the granularity of some milliseconds, and then you have sporadic events which happen when you hit the surface of Mars quite long in the future, or when the operator on your power plant console presses a certain button. Those are events which are very, very rare, and you have to embed these events into your overall real-time system in a sensible way. This is still doable, and we will learn techniques how to calculate that, how to calculate schedules which can guarantee certain behaviors, catering for just that. And again, textbook definitions, hard, firm, and soft deadlines. If you just read that, a hard deadline means a single failure leads to severe malfunction and or disaster. Crystal clear, right? That's a hard deadline. Firm deadlines, results are meaningless after the deadline, but they don't kill your system straight away. It's a firm deadline. You lose some feature, some functionality if you miss that deadline, but it's not disastrous. At least not if it doesn't happen all the time. And there's a transition, a gray zone here that some of these firm deadlines you can possibly violate once without any effect, but if you violate them 5 times, then something happens. And soft deadlines, results are still useful after the deadline. What does that mean? Yeah. Yeah, but what does that mean? You prefer?
Well, I thought all of this was a bit sort of, what is it all? Sure, yeah, there's like a hard everything breaks, okay. Then you have, to say it's a bit of a sort of spectrum thing where, there's always going to be a usefulness cutoff, and that can go down to some level. And in soft, it's going to be, it's nice in that way, but you still use it for something afterwards. It's not quite so good.
It's like you might be updating a value or something from a sensor or something, but you can still reuse the old data if you don't have the new data.
No, but that means it's useful after the deadline infinitely. So.
In our assignment, like we have visualized answers. What about like a frame rate?
No, your assignments lead to straight disaster. That's all hard deadlines.
So if you're updating a video display, it's not critical, but it's nice to have it.
Well, that's a firm deadline.
That's fair.
Because that's mission critical for the system. If I have a video player and my video player is not displaying any images, that's not a soft deadline.
No, but like if it's a frame behind, or if you're only rendering every second frame.
That's a firm deadline. So if it constantly breaks, the functionality is gone.
So it's a possibility that the soft deadline it may never happen.
Yes. Yes. And that means in practice, the term soft deadline is a euphemism for there is no deadline. Right? Because if I accept that this is never happening, results are still useful regardless when they come, 2 years later, then it's not a real-time system to start with.
You still have, for instance, you want to know the weather in France today, and you want to know by the end of today, because then it stops being the weather today, and you just learn it at 2 a.m. tomorrow. You can still have an idea about the general weather of France.
Sure.
It's not as useful as it was now.
Yeah, but then you lose your job as a weather forecaster.
Yeah.
Sure. So I think we can easily agree is late towards this whole thing. But how do you actually define for a practical system a hard deadline? How do you define disaster? Because that's so easy said. What is actually a disaster for your system?
You have to think about it a bit.
Say, oh.
You may
Okay.
That's what the job of the system is to do, right? So, like if you have like a temperature management system and its specs are to maintain the temperature within X degrees, then a failure would be if it exceeds that range.
Hard deadline is easy to define if something actually explodes. Then you know that if my system turns into flames, it's obviously that's triggering a hard deadline response, and I have to do something about it very quickly. But not many systems are of that character. It's usually much more mundane. Hard deadlines for most systems by default are those deadlines which are threatening your own system. So losing functionality in terms of my computer is about to be destroyed or becoming non-functional. It doesn't need to explode. It can also simply run out of battery. That's, from the perspective of your system, a disaster. Because you lose any kind of control when your system dies. For any of these systems, regardless whether it's in an explosive environment or not, for any of your systems, the highest and hardest deadline is self-preservation. Because without that, you cannot guarantee something else. Now, don't come with any self-sacrificing kind of scenarios that my machine is actually purposefully sacrificing itself for the greater good. And exactly. This is a nice philosophical excursion, but it doesn't really happen in practice. So if you have a system where you know that it actually is about to die, this is usually triggering a hard deadline straight away. Even higher than the thing exploding. Because if you're dead, you cannot prevent the explosion. So the first thing you do is you need to keep your system alive. If your computer is no longer there, nothing else happens. Which means trivially and surprisingly, most of these hard deadlines are usually related to monitoring your energy levels. If you're running out of juice for your machine, this is often triggering the hardest deadlines you can have in your environment. And sometimes triggering desperate operations. I adored the old approach in large mainframe systems where when the power goes down and the main capacitors are discharging, and you realize that my main capacitors in my power supply are discharging at the moment, so I have a few hundred microseconds left until the light goes out and my machine is actually dead, to switch over to utilize the momentum in your hard drive, to use your hard drive as a generator to power your mainframes back, because those hard drives were kind of beefy and there was a lot of energy in them. So using them to keep your machine alive, that's a very interesting hard interrupt you have there. Doesn't really work for our SSD drives, so this is a general idea. In practice, what actually constitutes disaster is, besides obvious cases that your airplane falls out of the sky or your power plant is about to explode, for anything more mundane and practical, it's not so trivial to decide which of those are hard, which of them are firm. How do you prioritize that? Because ultimately it comes down to you have to set priorities. And the priority levels are much harder to define in the real world than in textbooks, as you may be finding out. Okay. Any further questions on this general terminology? Not too magical, I think. So, languages and timescope support. Timescopes can be part of the language that you program and define these timescopes as a syntactical integral component of your programming language. You define that my task has to be activated at this time, has to run periodically, every so-and-so milliseconds, and has this and that priority, etc., etc. So all the scopes, all the time scope parameters can be part of your language. Could be part of libraries, or we do just plain causality analysis. Well, or we just have timing primitives, not actually time scope operations. What's the advantage of having time scopes as part of the language? Already says. Sorry. If you have the time scopes as part of the language, then all the analysis, whether the system actually can run or not, can be done directly by your compiler. Your language already knows all these effects, which is a pretty strong feature, which is pretty cool. Which means your compiler doesn't only tell you, yes, this can be executed, but your compiler can also tell you, yes, this can be executed considering the timing constraints which you gave to the whole thing. There is enough CPU power, there is a sufficient number of cores available that I can actually execute that. The whole schedulability analysis, does that fit together? Can I have 20 tasks which all want to run at 20 microsecond cycle times with hard deadlines associated with them? Can I do that? Does that fit together? The compiler will already tell you if this is part of the language, which is pretty cool. Huh? So, if you do timing analysis syntactically by some analysis tool, you need to be able to either solve the halting problem, which may be a bit of a harder side, or you need to be able to break down your statements into how long does it actually take and start accumulating and counting them up. For that, you obviously have to be a bit cautious whether this is still a Turing-complete machine. So what do? Everything which is not strictly time-bound, which is what? What constructs in your languages are not time-bound? No, not all loops.
Oh, like while loops, for example.
While loops, yeah. So loops which are differently, oftenly executed. If you have, for example, a for loop, there's no trouble with that, right?
As long as it's a real for loop.
The real for loop is...
I remember you lecturing me on this in first year when I said C has for loops, and you said no.
That's true, yeah. That's true. As long as it's the actual deterministic for loop where the compiler can decide how often that actually runs through, which is indeed not the case. So while loops are bad, and recursion is bad. Right? Anything else?
Like if it's Turing complete, it's probably a bad thing.
Now, is it still Turing complete if I kick out recursion and while loops?
Whenever you're waiting on IO, that's time window, is it?
Yes, that's a different form of analysis. That's schedulability analysis in terms of the interaction points between concurrent entities. At the moment, I'm asking for time predictable statements in the sequential part of your language. But from a purely sequential point of view, I think that pretty much covers it. So would you be willing to sacrifice recursion and while loops? For the greater good?
Good choice.
Like that and do whatever you want to.
Okay. And there are actual... thank you. That's very nice. There are... Whatever this thing is too long. Languages and suggestions to do that. Oh, I hope somebody's playing with electricity around this place. But maybe they do. I guess the hard deadline handler for the local power supply was not programmed properly. Fortunately, our laser projector survived. Oh, please. Thank you. Okay. So excluding those statements is one of the possibilities. You had another comment? No, you didn't. Okay. The other possibility is instead of removing them, attributing them. So you have, for example, a while loop construct where you say, yes, it is a while loop which runs normally as a normal while loop, but I also give this a timeout. So I have a maximum number of cycles or maximum number of times, a maximum time which are associated with that. If that's not fulfilled, I raise an exception and break out of that, which is this half-assed between these things, because it's still not an open while loop, but it can give you guarantees to do that.
Isn't that just a for loop with an if inside and a break?
If it's what?
Isn't that just a for loop with a if statement inside it and a break?
If it's limited by the number of iterations, yes. But we could also limit it by the total computation time. That's a bit of a different beast. But it's actually, in its very principle, it's not much different from that. Right. Okay, let's go through a few examples. Real-time Euclid. No go-tos. You're not going to whine. And no recursions. That's a bit of a sadder story. Loops are restricted to bounded loops, and all processes are static and non-nested. Then you can have attributes like this. My processes, or my specific process here, is associated with a periodic frame every 60 seconds, and this only happens after 600 seconds or when a specific external event happens. So you can have now a full time scope specification for every task you define. Would that be nice to have in Ada too? Do you have this in Ada? Not yet. There's light on the horizon though. One of my PhD students has been working in that field for a while, and as he is now working with Ada Core, there's also hope that this may change sometime in the future, and I would expect that full time scope interpretation of tasks will be one of the extensions for the next Ada standardized version, because so far we don't have this. Schedulability analysis is all on a fairly pedestrian level still on the Ada side. Okay. So what you do have at the moment, you can formulate, of course, the exact same thing on with an environment like Ada. It would look like this. So we are starting either when you have an external activation trigger or after a certain amount of time, and then you declare a constant loop there. This is also much boilerplate. This boilerplate can be done by the Ada compiler directly if you attribute that straight out. And B, if you attribute this, the much more important thing is that you can then also extract all these parameters and feed this into a schedulability analysis module straight away. That you not only compile that into that code, which is just convenience, but you can also give compiler warnings and errors if this cannot be executed, if this cannot be guaranteed to be schedulable. At the moment, this is all pedestrian. You would need to do this by hand. Okay. Real-time Euclid is a pretty old approach. It's not actually used at the moment. CRL is another one, complex real-time systems. That's a little bit more modern. And it also gives you full time frame syntax associated with your systems. All timing is verified at compile time. Cool. And even at runtime, you still check whether this can happen. And all your iterations and recursions are checked against upper bounds at runtime. That's a system which is compiled into C++ to be executed from there. The possibilities stayed pretty academic ultimately. It was not picked up in industry. But here we're coming to something which I've seen before, which I sort of dismissed as this is a pretty weird form of expressing it. But those languages had this from the very beginning. Perl always expressed time scopes as part of the language straight out, which is interesting that we are coming back to formulating time scopes with our mainstream real-time languages today, which has been happening for the last 20 years in all of these basic level real-time programming languages like Perl for a long time. And schedulability analysis here is possible, but not guaranteed by the language. It's not part of the language standard. Of course, Perl, coming from a German environment, they standardize things straight away, but this is not part of the Perl standard. Interesting combination of Perl and real-time Euclid led to high integrity Perl, but this is also just barely a standard which has, to my knowledge, not been picked up in industry in any sensible way. Distributed programming system. This takes it the full fine-grained way. It's interesting. What do you want to associate your time scopes with? If you have ever programmed in Occam, or have seen Occam programs, you know that the philosophy there is that all my concurrency expressions, all my asynchronous expressions, concurrency expressions are on a statement level. There is no differentiation between a statement and a process, which is very easy when you come from an algebraic point of view. A process starts from a null statement. That's a simple process. And then you expand your process with more stuff around. There's not the computer science concept. The process is what your POSIX interface defines as a thread, or what your operating system gives you as a process. From a mathematical point of view, there is no reason why you would have a minimum granularity for what you call a process. This is the approach taken here as well. Every single statement can have a time scope. I don't know how far this gets you in terms of schedulability analysis. Well, it's an interesting mathematical exercise. What is the right granularity for doing something like that? The granularity which we head towards at the moment is the granularity of tasks, processes. This is what you will mostly encounter in your ADA programming environment. This is where most of the real-time designs these days will put their time scopes at the level of full-scale tasks. How future-oriented that is, I leave to you to think about that, because the number of concurrent entities is constantly on the rise, and the concept of heavy-handed, full-blown tasks may not be the ultimate destination for these kind of scopes. On the other hand, it's probably not going to go to individual statements, but where the level in there is not quite so obvious. So this is actually an example where real-time Java was shining. Don't know whether it's still shining, because they have done a pretty decent job there. Defined a class scheduling parameters, and there's only one instance of scheduling parameters which has to be there, priority parameters. So that's the easy part. All of your real-time threads need to have a priority. Okay, so far. But then it gets more interesting. Then we have release parameters. And all the real-time threads need to have release parameters associated with them, which is the total CPU cost, which is associated with them, how long can they run, and a deadline, which you associate with them. If I'm using too much CPU time, I'm triggering an overrun handler. If I'm violating a deadline, I'm triggering a mishandler. That was the philosophy. So the basic parameters and the exception handling facilities, which is going with that, is an integral part of the specification of every real-time thread. So far, pretty cool. Now, being object-oriented, of course, we do the obvious and expand the release parameters by a number of more interesting ones. You have then periodic parameters that I have not only a deadline, but I also have a start time and a period associated with them. I have aperiodic parameters, which is the same as normal release parameters. I have sporadic ones. Minimum inter-arrival time. That's a parameter which you will see more of in the schedulability analysis. What does this refer to? Minimum inter-arrival time. You don't guarantee a specific cycle time, but you say that this event cannot happen more than every second or more frequent than 5 times a second. Between 2 events happening, there has to be a minimum time in between where nothing happens. You need a parameter of that sort. If you don't have this information, how can you possibly cater for that? Because this is a sporadic event, can happen anytime, as often as it wants. You say, well, schedule this yourself. How can I possibly cater for something like that? But minimum interarrival times give you the possibilities to do that. So now we pull this all together, and we get real-time threads. And real-time threads have now scheduling parameters, release parameters, and memory parameters. Now the memory parameters are a bit hairy, as you can imagine, because it's Java, and trying to get memory under real-time control here is problematic, which means the first thing you derive from the real-time threads, and what you actually use in real-time systems, are the no-heap real-time threads. And that the memory parameters are becoming a lot easier because they go away, because you don't have memory anymore. You just work with what you have allocated so far, and you stop allocating anything. You're not moving anything beyond that point. Which is, of course, a little bit non-Java, non-real-time Java, non-heap Java. Bit weird. But that's the only possibility how you can guarantee those parameters in a hard environment. Basically, you have to switch off garbage collection and any heap allocation in the process. So then we have a scheduler, and the scheduler has very interesting methods. Most interesting is feasible. So you throw all of these no-heap real-time threads with all the parameters at the scheduler, and the scheduler gives you the thumbs up. You can also run them as a side effect, but as a real-time guy, you're most interested in the thumbs up that it can be done, and then you're leaning back and saying, well, and then I can compile it to something which actually runs as well. Cool. But the most important thing is that you have a guarantee this can actually be executed. That's pretty nice. The only required scheduler is a priority scheduler in real-time Java. It sounds a bit dire. It's only a fixed priority scheduler, but realistically, most real-time systems don't give you anything else. Ada gives you a bit more. In Ada, you also have earliest deadline first scheduling and related scheduling strategies as a part of the default set, what you can choose from. But the bottom line for most real-time systems is fixed priority scheduling, and so it was defined in real-time Java as well. Unfortunately, a lot of things are not strictly part of the standard. For example, the overrun handler can or cannot be implemented depending on the feeling of the compiler constructor, which could be a bit of an issue. Unfortunately, real-time Java, other than that, is pretty much dead, I think, fairly safe to say. I think there's one surviving implementation, so maybe it comes back, bounces back again. The trend is more to have to push towards so-called real-time garbage collecting environments, and to use the full-blown Java environment and work on the garbage collection problem rather than on the language itself. And an active community, happily working. In hard real-time systems, none of that is actually used for obvious reasons. So that's still pretty far from that. And mostly also the real-time Java language as such has been labeled as soft real-time system capable. And so they've walked away from anything which is harder than that. Ada, there's not much there. You have just timing primitives. You have timers, yes, you have schedulers, but the timing attributes are not yet, at least, part of the language. So there is no schedulability analysis in Ada at all. This is all your homework to calculate that manually, and that can be very painful if you need to do this all by hand. A lot of tools can be handy: asynchronous transfer of control, timers, schedulers, tasks, and code interpretation. This is all very useful for the implementation side. For the analysis side, that doesn't get you very far. Okay. Or you say, who cares about time? I'm an SRL kind of guy, and I'm only caring about causality. Time is all zero-time assumption based to start with. If you have the luxury to work in that kind of system, your timing analysis is, of course, a lot nicer. The only thing you have to test here is actually causality rather than whether it's schedulable. Cool. That gave you a bit of an idea what are the parameters which we need to talk about and define real-time systems. And you saw that the technical field, how we can do that, is still a mix between academic, test phases, language extensions which are not really widely used in industry or accepted in industry yet. So this is a field in transition to define that. It's still mostly outside the main language specifications at the moment. Would you think it's a good idea to integrate that, to have this part of your language, or would you like to keep it outside of that?
I'm finding it nice to have concurrency type system. So maybe it could be.
Yeah. I mean, the more you have support from your compiler environment, the more you're getting spoiled about getting all this kind of analysis for free, if it can be embedded in there. But it will also make your compilers more and more of a beast. If you stuff all form of analysis into this one module called a compiler, this could get a bit unwieldy.
Could it potentially be that rather than having it all stuffed into the compiler, or like when it does all the compilation of the code, that it compiles it as it would otherwise and basically disregarding that particular scheduling information, but then saving all that disregarded information into another file which can then be later processed for separate.
Sure. I mean, this is exactly what happens, that compilers becoming more of a modularized operation these days, that you separate out some of the analysis parts which a compiler is doing today into separate parts. The same thing goes for dynamic flow analysis. Your compilers are estimating more and more for reasons of giving you error messages, but also more dominantly for reason of optimization. They do a lot of flow analysis along the line, and the flow analysis can of course be as big as you want. So this can be a gigantic module in itself, and this is more and more separate into separate modules. But how do you go about satisfying these requirements if you don't get just a single press button analysis of the whole thing? Plus, it doesn't really tell you whether this works on hardware later on. You still need to go a little bit deeper. So there are two different approaches, which I would label real-time logic approach and complex systems approach. You can do it all as formal and as mathematical as you can, as you wish to. Going into schedulability analysis, which we will do. Going into full logic analysis of your programs, which includes, just as a side effect, full verification of your programs to have a guarantee in which order this is going to be executed. And this gives you a correct solution with respect to your specifications. Cool. There's a great tick there. But in order to do that, as you can easily imagine, you need to have a lot of assumptions to simplify your problem to something which can be actually analyzed in a real-time logic environment and system. Which means electrical interferences, jitter effects, saturation effects, granularities, etc., are almost always excluded from those kind of analysis because they're just exponentially exploding your real-time analysis, your real-time logic analysis if you would include them. You need to cut them outside, otherwise your theory improvers just go back. Can't handle that. So you have to cut it down to a size where your theory improver will still accept that and still go through with that. Is that the solution? Or you say that I'm dealing with my design with a bunch of more approximate methods, but I take all of my considerations into it. This is more the engineering approach than the mathematical approach to it. This is not complete or correct in any formal sense whatsoever, but it can handle the real-time effects which you possibly want to handle, like jitter, etc. And you can do more rigorous experiments in that one. Okay, let's break that down. Complex systems approach. You calculate all your statement durations on your specific machine. You calculate all the loop iterations and recursions, program verification. You do a full deadlock and lifelock analysis, standard technology, which you have passed in the past someplace. Then you do your schedulability analysis of your system. So complex systems approach does not mean you're not doing your math homework. It means you're doing your math homework on a slightly higher level. You're not taking it on the strict logic level directly. You assume that your compilers are somewhat okay. Checking this dynamically at runtime and having fallback behaviors in case that you are still violating your behaviors at runtime. That gets us then to the reliability chapter, redundancy, fallbacks, emergency protocols. And this is, I'd say, how still 90% of all hard real-time systems today are ultimately designed. You try very hard with all the tools you have around, and then you assume everything goes still bad, and you have redundancy on top of the whole thing. Real-time logic, which we'll also get to some degree. You have to get most of the asynchronous behavior out of your system, which, for example, includes interrupts, which are one of the first things which usually go from your real-time logic analysis. You have to abstract away from them. All other kind of saturation effects, classical. If you do your who has designed PID controllers in the past? PID controllers? Yeah, okay. What do you assume if you design a PID controller? About the rest of the world? About your system? You don't assume anything about the rest of the world?
No, the one I did is just telling parameters.
Okay. Sure, I mean, there's the engineering way of designing a PID controller. The engineering way of designing a PID controller is to follow the tuning protocol. So you just let this thing run, and then you slowly nudge the parameters into the right way until it starts getting jittery, getting in oscillation, and you tune back a little bit. That's not what I meant. I meant actually designing a PID controller in a mathematical sense, that you derive it from some kind of assumptions. And the assumptions are what? What is the very idea of a PID controller based on? What do you assume about your system that you can mathematically justify using a PID controller? But your system is linear. Exactly. That's just for starters. So your system is linear, time invariant. Good. Keep going. Your system is linear, time invariant, and has no saturation. Yeah, but you do not model hysteresis effects or saturation effects because they are nonlinear effects which are not covered with that kind of thing. So linear, time invariant, non-saturating systems. On which planet do we have those? Not on this one. So this is a classical, very widespread, and very useful and productive set of assumptions, but we have to always be aware that this is a set of assumptions. And designing your real-time system in context of real-time logic is pretty much the same thing. You need to boil it down to something which you know is wrong, but you assume it's close enough. So it's a weird mixture of, I'm very strict mathematically, but I'm approximate with my assumptions. Then comes the fun part, part 2, verify my reduced systems. This is where you get your success threshold out of the whole thing, and you get the thumbs up that my system can be verified and all is cool. Then comes the pain. You compile this to an actual physical executable system. If you're lucky, then your system compiles automatically into something which can be run on hardware, which is pretty cool. But that's not always the case. And then comes the real pain part, namely you have to recheck whether any of your assumptions actually hold true. Because you verified your PID controller, for example, according to a number of assumptions you made there, and you will still, as an engineer, hold your breath when you actually run this for the first time. Right? You have this mathematical success story still in mind, and you loved how this actually, all your border diagrams and all these nice plots which you have done, and they have a nice safety margin. It's beautiful, but you still have sweaty hands when you actually let this engine run. Because you know that this is based on assumptions which are just blunt wrong, but hopefully close enough. And this is what you have in any real-time system which is based on real-time logic in the same way. Ultimately, what you do is you have to recheck your actual system. How do you do this? Complex systems approach. You do that, what you have been doing for 90% of your real-time systems already anyway, as part of that as well. So it's a combination of all of these effects eventually, and it's up to your individual system requirements where you put your emphasis. More on the formal mathematical side, more on the systems design side of systems. You feel at home more on the mathematical side? You enjoy proving things? Okay. That's good in a way, I don't know. Because if you go to industry, the one thing which you would utterly embarrass yourself with, which unfortunately I have seen with a number of people coming fresh from university, having worked in mathematical theory improvers of all sorts, and then they explain to their colleagues that they know what the optimum algorithm is, the optimum controller, the optimum approach for that one, because they have been proving in their environments that this is the optimal possible solution they can possibly get there. Never embarrass yourself in those kind of terms, because if you work with actual physical devices, you know that there is no such thing. Optimum means that you have made a lot of assumptions of which you know they're not true, and under those assumptions, this is the optimal solution, but only under those assumptions, not in the real world. In the real world, you still have to prove the pudding by having a test and running this whole thing and see how close you are there. I know this is brushing some of the more theoretically oriented approaches uncomfortably, but there's no such thing as an optimal controller in the real world. Okay. That made sense so far? Okay. This is all I wanted to say about time and space in this chapter. And you saw there were references in the previous parts. We will have whole chapters to dedicate to some of them. Obviously, we will have to talk about schedulability analysis to quite some detail. Scheduling is a good part of real-time system design, that you can guarantee that all of microcurrent entities can actually play together in a provable way, in a predictable and provable way. So we have to be very precise how to do that. And fortunately, very interesting and clever algorithms to do that, which is fun to work through. Sometimes it's surprising what things you can actually guarantee. And some things are quite easy to guarantee. Other things are utterly impossible to guarantee. It feels a little bit more like when you go for the first steps into computer science, you're surprised that some things are impossible. When you learn for the first time about the halting problem, you're a little bit on how hard can it be, until that actually sinks in, that these things are ultimately unmovable goals which I cannot get to. And other things can be proven and verified much easier than you thought. And schedulability analysis has a bit of a similar flavor to it. But the next thing which we are doing is asynchronism. I will do this after the break. And we have to understand very carefully what is the difference between all of our beautifully synchronized systems which we have been handling so far, and crudely, brutally asynchronous events, asynchronous things which we have to embed into our real-time systems, obviously, as well. So first we have to understand the nature of these asynchronous events. Most of you have been handling, or some of you have been handling interrupts in the past. That's a good starting point, that you have some idea about this. Everybody who has had 2300 will has some idea what interrupts are about. And you will also, of course, handle interrupts on your actual board. So this is a very practical implementation of asynchronous events, which you will see. Otherwise, please submit your stuff and enjoy 2 weeks of holiday, I hope, somewhat.